Good morning, guys, and welcome to today is actually March 10th. Today is Wednesday. This is covering problems from chapter 23 as promised, and actually it's raining outside today too, which is kind of fun. Anyway, so the problems I promised last time. Let me grab the book because hold on, okay. So we're doing problems from chapter 23, okay, and promise. I think we did problem 76, and I think we did it to a lot of extent, I mean in detail, so I'm hoping that you guys can go through those problems and basically analyze them, study them, and redo them, understand them, and do similar problems to them to reinforce what you've learned, basically, okay? The problems I promised that we will do for sure are problem 41, that's all from the 15th edition, okay? There was a question from one of you guys about problems from the e-text. If you don't have access to the 15th edition, you can go to the e-text and basically put the e-text as a resource and go to the section where it says, I think, problems and questions or something like this, and you're going to find these very same problems. And it's a quick way of doing it. Once you pull that, is just do Control F or find, basically, and you're going to find all of the problems. If you're looking for problem, for example, 61, which is another problem we're going to be doing today, you have to do in the search 23.61, and you're going to find it very quickly, okay? So that is basically because it's chapter 23, problem 61. That's how the book basically is organized. And then we did problem 76, so that's done. We are going to do also problem 77. So those are the four problems that I promised we'll cover. I mentioned also in class before, and I made the big fuss over problem 72 and 71. Hopefully you guys can do those. If you have difficulty with them, let me know. Problem 62 also for the Geiger counter. Problem 57, because problem 57 is an interesting application of this chapter in basically either chemistry, condensed matter, material science, doesn't matter. It's basically for salt, namely sodium chloride, and where you have actually sodium atom ions and chlorine ions, basically. One of them lost an electron, the other one gains it. One of them is positive, the other one is negative. And you're supposed to calculate the energy for the entire basically cell of the crystal, basically, in this case, okay? It's going to be a cube of size D, okay, width and height and length. You're going to find the energies for the system. So it's an interesting problem, and again, this is some of the stuff that's problem 46, which probably, I mean, this problem should be, for you guys, you should be able to handle, because it gives you a point charge of 5 microcoulomb, and then is held in space from a distance. They give you 6 centimeters from another sphere, so it's not another point charge, a sphere of with mass of so much kilograms, 10 to the negative 3 kilograms, or 4 grams basically, and another charge of 2 microcoulomb is fired toward the fixed charge with an initial speed. So I gave you the initial velocity. Gravity can be neglected. What is the acceleration of the sphere at the instant when its speed is 20 feet? You can use the conservation of energy for problem 46 basically, namely in this case, because there are no friction, there is no gravity, nothing else. The only potential energy in this case is the electrostatic potential energy. I'm talking about problem 46 if you didn't pick up basically the idea. So basically what you have in this case, you have 1/2 of mv squared minus the initial speed, which is 1/2 of mv naught squared, is equal to the final potential energy minus the initial potential energy, and basically you do the algebra, okay? You do the algebra and you have the gravity. So what is the acceleration if the sphere to the instant when its speed is, okay, so hold on, we need the acceleration, so that's not the conservation of it. Hold on, let's think about this problem. So we have a 5 microcoulomb charge is fixed in space from horizontal distance. So they gave us this distance. It really boils down to v squared minus v naught squared is equal to 2a times the delta x, the distance traveled. So that's basically the formula. From here, you're going to pull the expression. This is probably the first formula you have seen in kinematics, because this is a uniformly accelerated motion, which is really nothing but just the work energy theorem, or the potential energy too, however you're going to write it, okay? So at the end, this problem can be solved that way. Now, problem 41 is another problem that I promised that we will do, so let's get going, okay? Before I do that, there was something in the lecture that I promised that we will touch base on, and that is the electrical dipole. For the electrical dipole, basically, for the electrical dipole, we have this situation. Okay, we have a negative charge in here. Okay, let me find my pen. So we have a negative charge. So this is part of a lecture really, and we have a positive charge in here. The distance between the two, we took it in lecture to be 2a, meaning midway somewhere is a point of symmetry. So the whole distance is 2a, not the distance between negative charge and positive was 2a. So this was a q, and this is of course was negative q, and we were able to find per chapter 21 the electric field in the axis that joins the two charges. We called it the x-axis actually. At a distance x, we found the electric field on this side to be pointing this way. I know we didn't calculate it on this way, but if we did, it's going to be exactly similar, except that it's going to be pointing also toward the negative charge. Okay? We calculated it also from chapter 21, and this specific point in here on the axis of symmetry, the y-axis in this case, and we found the electric field to be pointing in this direction. And there was a characteristic for this electrical dipole, if you guys remember, and that was the P, which we call the moment of inertia, the dipole moment, I'm sorry, that's what we called it. For the electrical dipole, okay, the electrical dipole moment, which is nothing but the product of the charge times the whole distance. This is the whole distance between the negative charge and the positive charge. Okay, as a matter of fact, P is actually a vector, and it's equal to, in our case in here, in this symmetry only, because this is the I hat vector and this is the J hat vector, it's equal to the same quantity P times I hat, meaning that it's equal to, what is it, 2a times q in the I hat direction. It always points from the negative charge to the positive charge. So if you're given another problem where, for example, you're given the charges in space and they don't necessarily line up along the x-axis, they could line up anywhere on the plane actually. So, and that at that point you can find, and they were given the distance of course between the two charges. Let's say the distance between the two charges is, let's say for example, 2 centimeters. Okay, and the charges, let's for the sake of argument say that they are about 5 micrometers. Okay, so in this case I'm trying to find the dipole for this so q plus and q minus in magnitude equal to 5 microcoulomb, what I'm talking about here. These are charges. Okay, so the q in magnitude is 5 microcoulomb. So when you want to find the dipole moment for this one, again it's easy. P, this is 2a by the way, so if you're curious trying to find what a is, it's 1 centimeter. Okay, so the distance between the negative charge and the positive charge is actually 2a, and in this example it's 2 centimeter. So what is P in this situation? In magnitude is just equal to 2 times 10 to the negative 2, that's in meters because we want it in meters, times the charge in this case, which is 5 microcoulomb. Okay, if you do the algebra, 5 times 2, that's 10, times 10 to the negative 8, so it's going to be 10 to the negative 7, or if you wish, 0.1 microcoulomb meter. Okay, so that is basically what the dipole in here. You ask about the direction. Let's say for example in this example I give you this setup. Okay, the positive charge is this way, and the negative charge is in here, okay? And both of them are equal in magnitude 5 microcoulomb. So this is actually the direction. So I need the x coordinates of this point. It doesn't matter. Let's say, for example, it's 1 and 5. And this point is, for example, it looks clearly a negative 1, for example, and 1. Okay. So in this case, of course, this doesn't probably equal to 2 centimeters. Okay, and I need the units in here in the x-axis to make things happen. The distance in here clearly is equal to square root of the x-axis, which is 1 minus 1 minus 1, so that's plus 1, plus 5 minus 1, the whole thing squared. So of course this is going to be square root of what is it, 4 plus, and in here 16, so it's going to be square root of 20 actually at the distance if I did this example. And let's say, for example, the units are in centimeter. Okay, so this is square root of 20, or roughly about 6 centimeters something. Okay, is it? No, 4 centimeters something. It's just between 4.5 centimeters roughly. Okay, so I don't have the calculator before me, but that's probably what it is. Okay, because 4 squared is 16 and 5 squared is 25, so it's somewhere in between them. So in this case, so this is not, the distance is not 2 centimeters, but rather it's this number. Okay, so from here you can find what this, but I need actually the vector in here that starts from this coordinates negative 1 1 and 1 5. So I need that vector. Once I have that vector, I can divide it by its magnitude, which turned out to be 4.5 centimeters. So we have all of the information for P, basically, for in here to finding P, because we know exactly where the negative charge is and where the positive charge is, and this is where P is. So, and if the charges happen to be actually 5 microcoulombs, I multiply this number, I'm doing the proper conversions, and I'm in business. So that is a point that I want to emphasize in here, because I don't think that we did dwell on it as much when we did chapter 21, but it's still an important idea in here with the dipole, and we're going to see the dipoles time and time again. So here is the promise from chapter 23 though. Chapter 23 says that you don't necessarily, if you know the charges in here, you can find the electric field anywhere you wish. Isn't this powerful? Not only in this axis of symmetry, which is the x-axis or the y-axis as we did in chapter 21, which kind of was easier to some extent because we summed 2 vectors in here, but since we know the vectors are in the x direction, it was easy. And in here the y components canceled, and the only component that remained was the x-axis also, so it was kind of easy. Now in space, of course, anywhere in point in space, the electric field is going to be a complicated thing. It's going to be a complicated vector, really. So if we were going to go back, so let's go negative charge Q, positive charge positive Q. The distance between them is 2a. So in other words, this distance is a and this distance is a. And I want to go in space. I'm going to take this one as the origin of the axis. So this is 0 0 for all my coordinate system. So this is still the x-axis. This is still the y-axis. And I'm going to go to a point in space, this point specifically, whose coordinates are in the system x and y. So this vector, which I'm going to call r, is a coordinate for this point in space. So the vector r describes that vector, that point in space, and the point, of course, has coordinates xi plus yj. Basically, that's how we write vectors in general. Okay? It's just the sum of these 2 vectors, basically, the components of this vector. Anyway, so I'm interested in trying to find the electric field in here. Obviously, I can take the electric field due to this charge. And since this is positive, it's going to be pointing this way. I'm going to take the electric field due to this negative charge, it's going to be pointing this way. So if I were to do this with chapter 21, I really have to deal with this vector, that is E due to the positive charge. And then, so it's along this direction, by the way, and then another E along this direction due to the negative charge. And then find the projection of these 2 vectors and work my way through the algebra and do it. But that's not what we're going to do with chapter 23. We're going to actually use a potential, because the potential is not a vector, it's just a number. So we're going to find these 2 numbers and add them up for the potential due to the charge positive Q and the charge negative Q, and we are in business. Since we find the potential, we are midway finding the electric field. So again, this is a negative charge, this is a positive charge. The distance between them is still always 2a, so this is a, this is a. The whole distance is 2a. This is still my axis of symmetry, by the way. So this is still the x-axis. This is still the y-axis. And I'm going to go to that same point in here, whose coordinates are x in the x-axis and y in the y-axis. And I'm going to find the potential in this point. So I need this distance, okay? Potential doesn't care about the vector, it cares only about the distance. So v to the positive charge, which is simply going, since it's a point charge, q over 4 pi epsilon naught times 1 over that distance, r to the positive charge. That's why I put the plus in there. Same thing, I need, this is r to the minus the charge, so this is how far this point is from minus charge. So the potential due to the negative charge, the charge is negative, so I have to put negative in here, and it's a point charge, that's why I'm using this formula, and we found that for the point charges, divided by 1 over r minus. And again, we're in business basically. If we can find what r plus is and what r minus is, using the superposition, the potential in this case will simply be v plus v minus. Obviously v minus is negative and v plus is positive, so I have that q over 4 pi epsilon naught that is common to both of them. And of course I have to find the difference between these two quantities, 1 over r plus over 1 minus r minus. Okay, once I do find v, then of course I'm going to take its derivative with respect to the space variables with the proper sign, and I have found what that electric field is. Okay, so let's do that quickly in here. Okay, I know I promised we're going to do problems with this chapter, and we are. So this is basically the unit vector I hat. This distance, if you notice, this vector actually is a times I hat. So I have this vector a times I hat, and plus to it r, this r vector plus now. It's clearly from this geometry is equal to r. So I can see that r, which is xi hat plus yj hat, is the same thing that sum of this ai hat plus r plus as a vector. From here I can solve for r plus as a vector, which is going to be x minus a times I hat plus yj hat. All I did was transpose to the other side, and I have found r plus basically in terms of x and y. Good. Now I need to find this also r minus in here. So for the r minus, I notice the following from the geometry. Again, this is still pointing in the I hat direction, so this vector now has a length of a and direction of I hat. So this vector is 2a I hat. This is r. If I add these two vectors, I'm going to find r minus actually as a vector. So r minus as a vector is simply equal to a I hat plus r. R, remember, is just x I hat plus y j hat. So this is simply x plus a times I hat plus y j hat. Okay? Now I have both r plus and r minus as vectors. I need their lengths because this doesn't care about the direction, it cares only about magnitudes. So let's plug in the length now. The length for r plus is simply the square root of the x component squared plus the y component squared. And the x component squared is x minus a actually squared, plus the y component squared, which is y squared. So this is r plus. Similarly, r minus as a magnitude is the x component squared plus the y component squared under the square root. So it's x plus a squared plus y squared. Okay, good. So we have r minus and r plus in terms of x and y. Actually, a is just a property of the dipole in this case. So now v as a function of x and y is simply equal to q over 4 pi epsilon naught times open parentheses the inverse of this number, which is just 1 over square root of x minus a the whole thing squared plus y squared minus 1 over square root of x plus a times plus y squared, and the whole thing is closed in parentheses. So we have found the potential. Now, if you want to find the electric field in space, you can do the following. Ex is equal to, because it's a vector, by the way, E, so its Ex is going to be negative of dv with respect to x. So imagine with me you can do this derivative with a proper sign. And then Ey, you can do the same thing, which is minus dv over dy. Okay? So you can take this derivative with respect to y and do the difference and reorganize things. And now you have the x component and the y component of the potential anywhere you wish. I mean the electric field, that is. Anywhere you wish. Isn't this powerful? This is something we couldn't do with the simple geometries, and Gauss's law would not be very helpful to us also because we don't have any symmetry or anything like that. So there was an interesting case actually, and this is usually a typical homework problem, and that is for the dipole approximation, namely when the distances r is much bigger compared to a. Okay, so that was a study that we wanted to understand. This is, we called it the dipole approximation. And remember, in the both results for the case of the x-axis and the y-axis, we found that the electric field drops like 1 over distance cubed. Okay, because somehow these two charges are shielding one another. So their effect is a little bit diminished, and that's expressed in terms of that 1 over distance cubed. So this is the dipole approximation. So let's see in here how that can be worked out in this case. Okay. Well, let me go back into this expression for the potential then. So I'm going to express it not in terms of x and y at the end. I'm going to be finding it in terms of the polar coordinates, because that vector r can be also expressed in terms of its magnitude r and its direction with respect to the x-axis theta. And those are the polar coordinates that we're going to be using. So the vector r can be expressed in terms of those two terms too. So let's do that quickly. Of course, we're going to pull, there is an interesting thing in here that we're going to neglect any term in here of the order of a squared and higher, because a usually is a very tiny number compared to r in this approximation. So we're far away from the water molecule if we're studying molecules in general. Okay, so let's do that. That's where dipoles have applications in. So v in this case is going to be, again, q over 4 pi epsilon naught times square root of 1 over square root of, you have in here x squared minus 2ax plus a squared. I'm going to ignore a squared because it's small in this approximation, plus y squared. So I'm going to keep just the leading term in this case, which is x squared minus 2ax plus y squared, and there's the square root, minus 1 over the square root again of x squared plus, for the same reason, 2ax, dropping the a squared because I have actually x squared plus a squared, so a squared is neglected, plus 2ax plus y squared. Again, if you're not convinced, you can do a Taylor expansion in here, and you're going to exactly find the same result. So those are the square root. So this is not exactly equal, but it's valid in this approximation, in this dipole approximation. Okay. Now I'm going to take x squared plus y squared as a common factor because it's bigger than this a. So I'm going to put it from this square root. So it's going to be actually v is going to be equal to q over 4 pi epsilon naught times, open parentheses, 1 over square root of x squared plus y squared, that is nothing but r, times the square root of 1 minus, in this case, 2ax over x squared plus y squared, which is r squared, by the way. Okay, minus 1 over the square root of x squared plus y squared again, open parentheses, square root of 1 plus, in this case, 2ax over x squared plus y squared. It seems like all I did in this case is just pull 1 over r. Okay, let's get this 1 over r completely out because it's common to the two terms. And let's take advantage of the fact that 1 over the square root of 1 plus epsilon or minus epsilon is roughly equal to 1 over 1 plus or minus 1/2 of epsilon. This is by Taylor expansion for when we neglect epsilon squared. So, and then this is actually equal to roughly of 1. If it was plus, it's going to be minus. If it's always a minus, it's going to be plus epsilon over 2. Okay, if you're not sure about this one, you need to brush up a little bit on Taylor expansion or use it actually in here. Go to its definition, you're going to find the results in here. Okay, so we're going to take advantage of this approximation. And this square root, because this is epsilon now, because a is a lot smaller than r, So I know x and here are the same order of x, but one of the x is cancelled, the other one doesn't. Okay, same thing for the other term. Okay, so what's going on in this case? So the potential is going to be equal to q over 4 pi epsilon naught r. I put an r already, which is square root of x squared plus r squared. Okay, times open parentheses now of this has a minus, so it's going to be, the minus is going to be a plus. So it's going to be 1 plus 2ax over r squared, but don't forget that 2 in the denominator, that 2 in here. So there is a 2 in here. Minus, open parentheses, this guy has a plus in it, so this has a plus in it, so it has a minus in here now. So 1 minus, again, epsilon, which is this whole thing in here, which is 2ax over r squared, and then you have a 2 also in here. Okay, obviously the 1 and the 1 cancel, and the 2 and the 2 and the 2 and the 2 cancel, but I already have ax over r squared minus ax over r squared, which is 2ax over r squared. So the final expression for here is that q over 4 pi epsilon naught times 2a times x over r cubed. Okay, q2a, that's b actually, so that's why I didn't simplify it, times x over 4 pi epsilon naught times r cubed. This is the potential in here. Recognize the fact that x is just the x component of r. So r is actually, remember, is xi hat plus yj hat. And p is actually also, that p in here is the x component of p because it only has that. So the dot product of p times r is simply equal to px. Okay, so this is actually the dot product of that vector p and the vector r in general. So the result now becomes v is equal to p dot r. This is a scalar. This is the scalar product divided by 4 pi epsilon naught r cubed. In the polar coordinates, p times r, p is in the x direction, r in the y direction, and the angle between them is exactly theta. So this can be written as p times r times cosine of theta divided by 4 pi epsilon naught times r cubed. The r and the r cubed cancel, and we're left with an r squared in here, which means that the potential is dropping like 1 over distance squared. That means the electric field drops like 1 over distance cubed. So p cosine theta over 4 pi epsilon naught times r. Let's find r squared. I'm sorry. Let's find the quickly now the electric field in terms of polar coordinates in this approximation. So E is equal to minus in the radial direction the derivative of V with respect to R. Again, R grows by an amount delta R in the radial direction. So this gives me the electric field in here. So it's going to be actually equal to negative. The derivative of 1 over R squared is going to be negative 2 first, times the negative 2, so it's going to be a positive, times the negative, I'm sorry, it's going to be a positive, p cosine theta over 4 pi epsilon naught r cubed. The 2 and the 4 cancel, and we'll be left with p cosine theta over 2 pi epsilon naught r cubed. Okay, this is actually the same result. We put theta equal to 0 as the one we found in the lecture, in the chapter 21. Okay. This, of course, is not going to work for us if we plug in the value of theta equal to 90 degrees, because there is another component in here for the theta component, because there is another component in this direction, actually in the theta direction, and that is the one that we're going to find too. So, and this is actually this distance in here, r d theta. So this derivative in the theta component is going to be minus 1 over r times the derivative of v with respect to theta, and that is equal to the derivative of the cosine is going to be a sine. Oh, I'm sorry, I have to look at this. The derivative of the cosine is a negative sine times the negative, so it's going to be a positive also, positive p sine theta, and divided by 4 pi epsilon naught times r squared, that's r cubed. Again, if you put theta now equal to 90 degrees, this is going to be in the theta direction, which is the negative x direction, and that's exactly its magnitude too. So this confirms the electric field everywhere actually, and you can plot it and you should be happy with it. This actually used to be part of a homework, I think in the other book, not in this one, but it's hopefully you guys get the point in here that you can calculate the electric field anywhere you wish now in light of chapter 23, okay, at least for the electrical dipole. Okay, let's go back into our problem. So the problem we did so far, so this is part of the lecture that we didn't finish. Problem that we did so far, problem 76. We're going to tackle problem 41, then 61, then 77, and that is actually part of the stuff that we promised we will do. So problem 41. Problem 41 says the following. You have a metal sphere with radius RA is supported on an insulating stand at the center of a hollow metal spherical shell. So basically I have a sphere. It could be solid, it could be hollow, it doesn't matter because it's conducting, so there is no charge inside anyway. So that's basically what we know about metals. So this has a distance of RA, and there is a bigger sphere in here. This is hollow now, of radius RB, okay, and the inner sphere has a charge of positive Q. So the charge on the conducting sphere has to be on its surface in here, okay, and the outer sphere has a charge of negative Q. And they want us to do what now? Calculate the potential V sub R for R less than RA, and for R more than RA but less than RB, and for R greater than RB. So we want to find V as a function of R for the following scenarios: R less than RA, R more than RA but less than RB, between the two spheres basically, and R more than RB. Okay. They tell you specifically in this problem, take V to be 0 when R is infinite. So when R goes to infinity here, we want V to be 0. Okay, so that's easy. So we want the potential in here to be 0 at infinity, far away from the charge, from the the charges, in this case the spheres. Okay, so we want to find the potential because there are no charges inside here. If we use Gauss's law or whatever you want to, you're going to find that there is no electric field. Since there is no electric field, the integral of 0 is going to be a constant. So we know V inside is going to be just a constant. I'm going to call it C1, okay? I don't know what that constant needs to be. What is it? But I need it, and I know exactly how it needs to behave. It has to be so that the potential function V sub R everywhere is going to be continuous function, okay? So, but the reason why I'm fixing it so that it's not 0, because I know that the potential is 0 somewhere else. So I can't have two 0 potentials in here, at least by definition. Maybe another one will come up as a matter of calculation, but not as a matter of choice. It's already chosen for you. You can't make that choice again. Okay. So that is that thing. In other words, this is basically a multimeter. Multimeter has two ends in it, okay? This is the multimeter. Okay, it has two ends in it, and it can be, you can put this one somewhere as being the origin of the voltage somewhere. You can't put it everywhere. You can only put it in one point. This one will be the voltage somewhere else. Now the voltage for this one might come out 0. That's another situation. But that's because probably you're on some sort of an equipotential or something. But that's another issue, okay? Now the potential between A and B, now that's another thing. The charge is Q enclosed, okay? So actually I can treat it now. The whole charge is centered in the same point, and this is to some extent similar to a point charge. And at the distance r from a point charge is a charge enclosed Q over 4 pi epsilon naught, albeit it's a sphere, and the distance is r, so it's 1 over r. But now I have to add a constant, and again I don't have really a lot of choice on that second constant now, because my choice is taken already. It's stated already. I cannot make C2 equal to 0 because I cannot go to infinity because I am somewhere between the two plates, the two spheres, I'm sorry. So the last thing in here is the potential outside. the potential outside also is going to be a constant because of the fact that in here, if I do a Gaussian surface, the charge enclosed is 0 because positive Q and negative Q is 0, so E is 0 in here. Since E is 0, the integral of 0 is another constant in this case, which I'm going to call constant C, or C3 if you like, it doesn't matter. I know this constant now because I know the potential at infinity is 0 and the potential is constant everywhere in here. So if it's 0 at infinity, it's 0 everywhere outside in here. So this is 0. So that is how I can basically find that constant now, those constants. So I know the potential is 0 everywhere, I mean outside of the, far away from the sphere, but it's the same everywhere outside of the sphere. Since it's 0 far away, it has to be 0 everywhere up to the point where the sphere comes into contact with it. So which means that this potential at point RB must be also 0. So V sub RB from the inside to satisfy the condition, since it's 0 everywhere, and just in the contact of RB, that too is 0. So V sub RB is 0 at that point. And V sub RB, I can use the expression from the inside to find it, which is Q over 4 pi epsilon naught times 1 over RB plus that constant C2. This must be 0 to satisfy the condition. Now here, then I have a condition for C2. I can find that C2 is equal to minus Q over 4 pi epsilon naught RB. Now I have found this constant, so I can go and plug it back into this expression, and I know the potential inside now between R, A, and RB, and that potential now is well defined as a function of R, is equal to Q over 4 pi epsilon naught times 1 over R minus 1 over RB. Anywhere between the two plates, as long as R, between the two plates, I'm sorry, between the two spheres, as long as R is greater than RA but less than RB. So that fixes that problem. We have to go to the same point in here of contact at the point RA and require that 2 is continuous. It's constant the same way everywhere in here, C1, but I know its value on the other side. So at RA, the same situation, at RA, the potential is V sub RA on one side, which is equal to Q over 4 pi epsilon naught times 1 over RA minus 1 over RB. And that potential must be equal to constant from the other side, C1. So now that is that constant. So now I have the potential everywhere because I can find all of its values. And it's a continuous function. I mean, its derivative may not be continuous, but that's another thing. So the potential is equal to that constant, which is Q over 4 pi epsilon naught. We should have taken Q as a common factor because it's everywhere the same thing. 1 over RA, 1 over RB, which is a constant when R is less than RA. It's Q over 4 pi epsilon naught times 1 over R minus 1 over RB when R actually is more than RA but less than RB. And it's 0 for R more than RB. Okay, so this is basically the solution to this problem, and it's all of the three cases listed in there. Hint, the net potential. Show that the potential of the inner sphere with respect to the outer sphere is this much. Okay. We want to find the difference in potential between the inner sphere and the outer sphere. I know the potential in here. It's actually V sub RA. It's this potential in here. And I know the potential in here. It's actually 0. So the difference in potential between A and B is actually the potential at RA, which is actually this number, minus the potential at B, which is actually this number. So it's going to be Q over 4 pi epsilon naught times 1 over RA minus 1 over RB minus 0. And that is exactly what we're supposed to show, that VAB is equal to Q over 4 pi epsilon naught times 1 over RA minus 1 over RB. This result is important for later on when we consider spherical capacitors. Okay, that's what we were supposed to show. And then and the result, use equation 2323 from the result to show that the electric field is given by that expression. Okay, using that relationship between, of course, the spheres. They wanted between the spheres, this one. So for that, we're going to take the derivative with respect to R. That's what 2323, by the way, is. So the electric field in the radial direction is minus dV over dr, and that is equal to minus, of course, the derivative of a constant is 0, so the only thing I'm left with is derivative of 1 over r, which is negative 1 over r squared. cancel the negative in here, so it's going to be a positive Q over 4 pi epsilon naught times 1 over R squared. Okay, this is for R more than RA, but less than RB. That's how they want it. However, they want this expression to be expressed in terms of the potential, because we know Q over 4 pi epsilon naught in terms of VAB, so we can basically sub this value using that expression, and you can do the algebra quickly in here, and you'll find that ER is VAB over that 1 over RA minus 1 over RB times 1 over R squared, just by working this thing. So if the potential is known and the size, the physical size of these things is known, so we really don't need to know the charges in this case. Use equation 2323 and part of it to find the electric field that points outside of the sphere of the center R. Okay, if we take the derivative, basically take the derivative of this potential for R greater than RB, and the same derivative, by the way, this one, and to show that the electric field is 0. So the derivative of 0 is 0, so there is no point of really doing this part. And then the last part of this problem is, suppose the charge on the outer sphere is not actually minus Q, but rather it's a different charge. So this is not a typical problem for capacitors, so this is a different issue. And you're supposed to find basically where it's going to be shifted a little bit by that negative value that is the difference between the two charges. I will leave that part to you guys to finish it. Okay. Again, part of your assignment for this one is to verify all of my calculations, make sure I didn't miss some minus sign here or there, or 1/2 or a pi or something. And actually, if I made a mistake, please let me know, because again, I always make mistakes. So please correct them and let me know so that we can have this fixed. And you're supposed to redo these problems anyway on your own. Okay. So this is finish the last two parts. Okay, and check my work. If there are numbers, you're going to do the numbers. Okay. Problem 61. Problem 61 have two coaxial cables identical to this problem, except that instead of the spherical geometry, you have now cylindrical geometry. That's all. So you have an inner sphere, cylinder of radius A, and an outer cylinder of radius B. And they're very long, okay, so that you can use basically the electric field they produce in one point in here from this one, or this one in this point, is simply given by that expression, which is lambda, where the lambda is charge distribution divided by 2 pi epsilon naught, the distance in here, whatever that distance is. Okay, so that's what we found in lecture. So we're going to use that result in here in this case to find basically the electrical potential, because we want to find the potential. So calculate the potential V sub R. So this one has a lambda on it, positive lambda, and this one has a negative lambda. You can clearly see that the electric field will be pointing in this direction. Okay, so it's from the inside to out. Okay, so this should be of a higher potential, V high, and this is V low. Okay, so this is where you put the COM port. The inner one is where you the outer one is where you put the COM port, and the other one is where you move it all the way inside. Okay, anyway, so calculate the potential V sub R for R less than A, for R greater than A, and less than B, and for R bigger than B. Okay, the potential. So we can clearly see in here that inside, because there are no charges enclosed, and again they tell you that take the potential far away to be 0. So we know the potential in here is 0 by choice. So I cannot choose it to be 0. I need it to be a constant in here. And in here I have to integrate this expression because I know the electric field is not 0 in here. Again, if I use the Gauss's law in here, no charges enclosed divided by epsilon naught, so they call the electric field. So there is no electric field in here. So E is 0 in here. And let's find now this stuff in here that says the E also is 0 outside too, because the charge enclosed is 0. We have negative lambda per unit length and positive lambda per unit length. So no matter which length you have, you're going to have 0 charges enclosed. So in between them, at this distance, so now when R is bigger than A but less than B, then the electric field has this charge distribution in here in it, and we are going to use that expression at a distance r from the center is going to be basically lambda over 2 pi epsilon naught times r. Okay, and this must be equal to minus dv over dr because there is no angular dependency, so the partials become just straight derivatives in this case. So now let's find what the electric potential now need to be. So V is going to be the negative, the integral over 2 pi epsilon naught of dr over r. Okay, and that has a natural log in it, so it's going to be a minus lambda over 2 pi epsilon naught times ln of r plus constant. So this was C1, so this is another constant which I'm going to call C2. Okay, and I know the potential outside is going to be also a constant. So the potential outside, because no charge is enclosed, is going to be a constant, and that constant better be 0 because again the potential is 0 far away, and it's constant everywhere all the way to the point where we get into the surface of the outer shell. So in this case it's going to be 0 at that point too. So the constant is 0. I will use a continuity in here to find what that constant is for constant 2. So I'm going to require that V sub b, which is 0 on one side, must also be equal to minus lambda over 2 pi epsilon naught ln of b, I'm sorry, I call it b in here, plus C2. So in here clearly C2 then is equal to lambda over 2 pi epsilon naught ln of b. Okay, which means that inside then, between the two wires, what we have in here, between the two cables basically, what we have in here is that V sub r is equal to simply this log minus this log. The coefficient is the same, so the coefficient is lambda over 2 pi epsilon naught, and I'm going to use a definition in here, or at least the property of the log, which is give me the ln of b over r. Okay, so that is basically what the potential is. Note that the potential is positive indeed, because as you move away from r, this number is actually getting, b is always bigger than this number, so the potential is actually positive and going all the way to 0 at the end. Okay, so the potential, now I need to find the last constants in here, which is C1, and again I require the continuity in this point, so the potential on one side is equal to C1, I'm sorry. So V of A at some point it's C1 on one side, and it's also equal to lambda over 2 pi epsilon naught times ln, replace r by A, and you have the result. So this is basically C1. So we found the potential now as a function of distance everywhere. So the potential V sub r is equal to lambda over 2 pi epsilon naught times, open parentheses, for r bigger than b, it's 0. For r less than b but greater than a, it's equal to ln times that number, of course, of b over r. And for r less than a, it's a fixed number, it's ln of b over a, because a and b are fixed. So that is the potential in here everywhere in space as a function of distance r. Okay, and show that the potential between the points a and b is that lambda over 2 pi epsilon naught, that value. Okay, again, we want to find the potential between the inner and the outer. So we want to find VA minus VB. That is what they mean by VAB. It's the difference in potential between them. VA is this number, actually. It's ln of b over a times that lambda over 2 pi epsilon naught, I'm sorry, minus VB. VB is exactly 0. It's this value. So the difference between them, again, is simply equal to lambda over 2 pi epsilon naught ln of b over a, because b is greater than a. This is a positive number, as expected. So the higher potential is where this side is, and the low potential is directly, that's 0, and we're in business, because the log of a number that is bigger than 1 is always positive. Okay, then find also the potential, the electric field between them using that same equation 23.23, and basically find the potential in between them in terms of the potential, not in terms of lambda, which is interesting because we found the electric field in this expression in terms of the in terms of lambda. So we really want to express it in terms of the potential, which is something we can measure with a voltmeter, okay? Something that we can do in the lab. So again, we're going to find that expression in here. The electric field is equal to minus dV over dr, and it's equal to, between them of course, so we need to find the expression between them. It's minus, the derivative of a constant is positive, it's 0, and the derivative of 1 over r, okay, so minus the derivative of length, so it's going to be a minus, first of all, from the definition, of lambda over 2 pi epsilon naught, and you have a minus in here already, because this is minus ln of r, so it's going to be a minus 1 over r again. So the minus and the minus cancel, and we're back into business that we basically started with, that the electric field is lambda over 2 pi epsilon naught times 1 over r. Now, this lambda over 2 epsilon naught is related to the potential that you can measure in the lab with that stuff, so with the ratio also of the geometry in this case. So lambda over 2 epsilon naught is simply VAB over that log. So if you sub in it, you're going to find the electric field now expressed in terms of the potential as VAB, the potential between the inner and the outer cables, divided by the log of their radii, the ratio of their radii, the outer of the inner, times 1 over r. That's an interesting result in here, okay? So that's problem 61. Problem 76 we did together. Problem 77. Problem 77, basically, that's the last problem in here, in this sequence. Problem 77 gives you a region, the electric field in a region that is within 2 meters of the origin of a rectangular coordinate system is given by. So they gave you the potential now. They tell you the potential is some function of x and y and z, and it's actually equal to a constant a times x to a power L plus a constant b times a y to the power m plus a constant z times constant c times z to the power n plus a constant d. Okay, so this is an approximation for the potential. Basically, we want to model it after this dependency, where a, b, c, d, l, m, and n are constant. The units of a, b, c, and d are such that x, y, and z are in meters, and the v is in volts. Okay, so it's clearly v is in volts and d must be in volts. A is in the units of 1 volt over meter to the power L. B is in the units of volt over meter to the power m, and C is in the units of volts over meter to the power n, whatever that L and m and n are. Okay. You measure the voltage on each table and you find the following. So you have 4 points in here. For each point you are given 3 values in here, or 4 values actually, I'm sorry. 1 for the voltage and 3 for the x and y and z components of the electric field. So you have plenty of equations in here. You have 4 times 4 equations. You have 16 equations to solve to find 1, 2, 3, 4, 5, 6, 7 unknowns. So you have plenty of equations to find your unknowns in here. Okay. Obviously, some of the 16 equations may be just a linear combination of previous ones. So this is not a completely basically it has enough equations for it to solve the problem. So let's do that. Okay. So let's find this unknowns. First point, they tell you in the points 0, 0, 0 you use the voltmeter. Okay. And you find V to be exactly equal to 10 volts. Okay. But if I plug in into this expression, I have a to the power times 0 to the power L plus b times 0 to the power m plus c times 0 to the power n plus d is equal to 10. So we know exactly that d is equal to 10 volts. End of the story. So that answers one of the unknowns. Let's do second point. The second point has coordinates basically in space that are the points 1 meter, 0, 0, and the voltage there is equal to 4 volts. Well, if I go into this expression, I have A times 1 meter to the power L plus B times 0 to the power N plus C times 0 to the power N plus D, which is 10 volts. This must be true. Therefore, first of all, I need to move 4 to the other side, and this is going to give me negative 6. So negative 6 volts must be equal to A times meter to the power L. So A, I know its value. It's negative 6 volts per meter to the power L. Okay? I don't know what L is, so I really don't have a full answer to A. So I really need to find what that L is. So for that, there is another point that was given to you in this case. Actually, the points that were given to you, I misstated them. So yeah, there are 16 values, but don't forget that all of the others are zeros, so they don't help you much. The points that are given actually are 4 points for the volts and 3 points for the electric fields, for a total of 7 equations with 7 unknowns. So you have plenty of equations to solve your system. Okay. So they tell you the electric field in that point is equal to. The electric field would not have helped us in the first one, because if we took all of these derivatives, they tell you it's 0. So it's not going to be helpful. It's going to be 0 equal to 0, which is an identity. So that's why we have a bunch of equations, more than what we need, but a bunch of them are just identities or trivial equations that don't give us more information. So that's why we couldn't use the next 3 values for the electric field in this point 0, 0, 0. But in here we have another interesting point. In here we have actually 4 values, but only 2 of them are useful. The other 2 also are going to be trivial values, so they are not going to be useful to us. So that's why we really have 7 equations with 7 unknowns, not 16 equations with 7 unknowns. Anyway, so what we have in the second one in here, we have the electric field in the x direction is minus dV, by the way, with respect to x, and that is, if I look at that expression in here, it's going to drop in L times A times x to the power L minus 1, and these are going to not matter, because if I take the derivative of y with respect to x is 0, the derivative of z with respect to x is 0, the derivative of d with respect to x is 0, because all of these are constants when it comes to that point. So basically the electric field is going to be minus A times L times x to the power L minus 1, and this obviously is evaluated at that point, okay, namely this one. So this is equal to, so minus A, I know what A is, it's negative 6 volts per meter to the power L, okay, times L, times x, and x is 1 meter to the power L minus 1 is equal to 12 volts per meter, okay. Meter to the power L and meter to the power L cancel, and I'm left with a volt that cancel with a volt, and I have 1 over meter in here, because negative m to the negative 1 is actually 1 over m in meters. So that 2 cancels this one, so I'm left with the equation that negative times negative is 6 times L, 6L equals to 12, and that gives me L equals to 2, okay. So we have L equals to 2. So we have both A as a function of L. So now I know exactly what A is, actually, because I know that L is equal to 2. So I know that's negative 6 V volt per meter squared. Okay. This is basically going to repeat itself time and time again to find the rest of the others. Basically, you go to the next point, which is of coordinates 0, 1, 0, and you do the same thing to find both B and M. So let's do that. Okay. For the point of coordinates 0, 1, 0, we know the potential is equal to 6 volts. So I'm going to put 6 in here. Volts is equal to, obviously, the point x equal to 0, so it's not going to contribute in here. So I have A times, which I know its value, actually, it's negative 6 volt per meter squared, times x squared. But x is equal to 0 in this point, so we don't care for it. So it's going to give me 0. Plus, now I have B times 1 meter to the power m. Plus, again, 0 for C, so it's 0. Plus D, which is 10 volt. If I move 10 to the other side, I'm going to find negative 4 is equal to B times 1 meter. This is volt, by the way, to the power m. So that means that B is equal to negative 4 volts per meter to the power m. Please don't confuse these two m's. One of them is supposed to be a number, and the other one is actually a unit for distance. So this is, if you want to put it in between parentheses, it's the meter to the power m, not the volt to the power m, okay? So that is this part. Now we're going to find the electric field in a similar fashion by taking the derivative with respect to y. And again, the derivative with respect to y, the only that's going to be left is the one for the second term, which involves y. So it's going to be minus m b times y to the power m minus 1. And this, according to that point, it's minus m times minus 4 volt per meter to the power m. This m and m are the same, but this one is a unit for distance, okay? Times this y is 1 meter to the power m minus 1. Actually, this m and this m now cancel completely. I'm just left with a volt over meter in here. Must be equal, according to this data, also 12 volt per meter. Again, the volt and the volt cancel, and this last meter and this last meter cancel, and I have at the end 4m equals to 12, which means m is equal to 3. So in other words, that B now we know what it is, because B is negative 4 volt over meter to the power m, and m is 3, so B is equal to negative 4 volt meter cubed, okay? So if I go back, now I have B, and I have m. So the expression now starts to become clearer and clearer. So x, remember, is equal to negative 6 volt per meter squared, negative 6 volt per meter squared, times x squared, and then here negative plus, if you wish, negative 4 volt per meter cubed times y cubed. Let's find C. And now don't forget that we have found D already to being 10, okay, volts. So the last two terms are C and Z. And for that, we have another point in here, actually, the last point in here, which is 0, 0, 1, okay? So the point of coordinates, again, 0, 0, 1. We have the volt in there is actually equal to 8 volts, and that is equal to 0 plus 0. Those are the x and y coordinates. So we're left with the last one, which is C times 1 meter to the power n, plus, of course, the 10 volts from the other side, is equal to 8. So if I move the 10 to the other side, I'm going to find negative 2 volt is equal to C times 1 meter to the power n, which means that C now is equal to negative 2 volts per meter to the power n. But I don't know what n is, so I really did not answer this question, at least for this point. Let's find the electric field along the z direction, and that is equal to, again, the negative derivative of v with respect to z, and everything else doesn't contribute with the exception of the component for z. So I have n times c times z to the power n minus 1. So it's going to be a negative nc times z to the power n minus 1. And again, all I have to do is sub this value and equate it to the electric field, which is 12 in this case. So the electric field is 12 volt per meter. And this must be equal to negative n times c. C is negative 2 volts per meter to the power n times the distance. And the distance is actually 1 meter. And the whole thing is to the power n minus 1. This power and this one cancel because both of them are meter to the power n. This volt and this volt cancel, and this volt meter and the last meter cancels, and I basically have 2n is equal to 12, which means that n is equal to 6. So now, not only I know what n is, but I actually know what c is. C is equal to negative 2 volts per meter to the power 6. So the final thing in here for the electric potential is plus minus 2 times to the units volt per meter to the power 6 times z to the power 6 plus 10 is equal to a constant. So now we have the entire electric field, electric potential, which is v sub x and y and z and equals to a is it what? It's negative 6 volt per meter squared, negative 6 volt per meter squared times x squared plus b, which is negative, was it 4? Oh no, I went too far. -4, and the other one is -2. So -4 volt per meter cubed actually times y to the power 3 plus the other one is -2 volt per meter to the power 6, and it's in here actually, you can see it, z to the power 6 plus 10 volts. So that's basically how the potential look like, and they want us to find it now. So use the data to find A, B, C, D, L, M, and N. What are V and the magnitude of E at the point 0, 0, 0? So E is given. If I plug in 0, 0, 0, V sub 0, 0, 0, that is simply equal to 10 volts. Okay, that's actually one of the data that was given to me. What is the electric field in that point? The electric field is actually given to me also as 0, 0, 0, 0. Let's check it, okay? E is equal to minus the derivative of V. So, I'm sorry, let's write it. E is equal to minus the derivative of V with respect to X, minus the derivative of V with respect to Z, minus the derivative of V with respect to Y, I'm sorry, with respect to Z, the last one. So it's going to be a minus, open parentheses, the derivative of this guy with respect to X is going to be minus 6 times 2, that's 12, 12x. Okay, I'm going to leave the units for right now because it's going to be volt over meter everywhere, okay? Okay, minus 3 times 4, that's 12 also, minus 12, again, y squared. And again, 6 times 2, that's a -12 also, z to the power 5. Okay, so the electric field in general is going to have that 12, nice 12 in it. So it's going to be a positive 12 times x times y squared times z to the power 5. Okay, so they want to find E at 0, 0, 0. That is going to be 0. If you sub in 0 everywhere, it's going to be 0. Okay, now they want to find V at that point, half, half, half. So V, first of all, at half a meter, half a meter, half a meter. I'm going to leave this algebra for you guys to go into this expression and sub half everywhere. So basically, it's going to be a negative number in here, 6 times 1/2 squared minus, I forgot, 4 times 1/2, so squared in here, minus 4 times 1/2 cubed minus 2 times 1/2 to the power, what is it, 6 plus 10. Okay, so we're going to add up all of these numbers and we're going to find the answer in volts. Okay, volt. The same thing, the electric field is going to be equal to 12 times half, half squared, and half to the power 5, or 1 over 32. Okay, don't forget the units. Okay, so this is going to be in volt over meter. And finally, the point 1, 1, 1. So that's probably easy to calculate. Let's see if we can do that. So V at 1, 1, 1. So it's going to be, again, negative 6 times 1 squared. That's negative 6. Negative 4 times y cubed. That's negative 4. Negative 2 times 1 to the power 6. That's negative 2. Plus 10. So this is negative 10 plus, so it's going to be negative 2 volts. Okay, that's easy. The electric field also should be easy to calculate in this case because I have to do the powers of 1. It's so easy that even I can do this. So it's 1, I have 1 squared, 1 to the power 5, and it's going to be just 12 times 1, 1, 1, and it's a positive number volt per meter. Okay? So don't forget that you have to finish the calculations, and if you have any questions, please let me know. I'm going to stop the recording right now, and I trust that you guys are going to do these problems, and also at least we'll start working on the other problems I told you about. If you have difficulty with them, please let me know, and we can work out whatever difficulties you two guys have, and maybe speed up the discussion later on. Thank you.